everyone for coming. We have now started our testing and verification session. We have a lot of amazing papers that is going to be presented here. I'm very excited. So just without any delay, let's introduce our first speaker, Kiran. He's going to speak to us about Sisyphus, mostly automated proof repair for verified libraries, also a distinguished paper in PLDI.
Okay. Should I start? Yes. Okay, perfect. Thanks. I'm pleased to present this. Hi, I'm Kiran. I'm pleased to present this work. Sisyphus, mostly automated proof repair for verified libraries. There was a bit of an echo. Okay. So, without further ado, let's get started, and let's write a program. So just to keep things interesting, today we're not just going to be writing a program, we're going to be writing a verified program. And more specifically, our programming task is to write a function to convert a sequence to an array. So sequence here refers to OCaml's sequence data type, which is a sort of lazy list. And a sequence is nothing other than a function, unit to node, that can be evaluated or forced and will return either a nil or a cons of a head and a lazy thunked tail. So for example, to represent a sequence containing 1 and 2, we can simply use the following expression. Okay, so with the preliminaries out of the way, let's write some code. So our function, let's call it toArray, takes as input a sequence S. And the first thing that we're going to do in our implementation is we're going to force the head of the sequence and branch on whether the sequence is empty or not. So if the sequence is empty, then our implementation is trivial. We can just simply return an empty array. In the case where the sequence is not empty, well, then we're going to first calculate the length of the sequence using a helper function. And then we're going to, once we know the size, we can allocate an appropriately sized array, passing in the head of the sequence as a default value. And now to populate the array, we're going to use a helper function, iterI, that traverses over the sequence, calling a user-provided function at each element, passing in the index of iteration I, and the current element being visited VL. And we simply use these two values to insert the element into the corresponding location in the array. And then to complete our function, we just need to return our populated array. Okay, so we've written a program, but remember, our goal is not just to write a program, but a verified program. And if we want to verify a program, we need some kind of specification with respect to verified. And so we'll use the following triple, which simply asserts in its precondition that our input is represented by this logical predicate sec, which simply asserts that it is a sequence and that its contents can be represented by a logical list L. And assuming this precondition, then our postcondition simply asserts that the return value of our function, captured here by this existential parameter A, will be a value that points to an array on the heap whose contents is also modeled by the same logical list. In other words, it captures exactly what it means for our conversion function to be correct. So now that we have a specification, let's look at some proofs. So our goal is to verify this program with respect to the specification I just presented. And to do this, we're going to make use of a particular separation logic-based embedded verification framework in COC, CFML2, that is particularly tailored for reasoning about these kinds of mutable OCaml programs. So using this framework, we can verify our program using the following proof script. So I'm not going to go through the steps of this proof in detail, but the high-level idea is that the proof mostly mirrors the intuition I presented earlier. So we symbolically evaluate the program using dedicated tactics for each program statement, and thereby reason about the symbolic state and establish the postcondition. One thing to note in this proof is that we're making use of the assumption that all of the other functions that we call have been already verified elsewhere. So for example, length. So overall, this proof is fairly straightforward. The main non-trivial aspect is the call to this function iterI, because iterI is a higher order function, and so its specification requires us to supply an invariant to describe how the state of the heap is persisted over the course of the iteration. In this case, parameterized by this value t that represents the prefix of elements that have been visited so far in the iteration. And in this case, the proof engineer who wrote this script has somehow come up with this invariant. I'm just going to show it up screen here, which essentially states that over the course of the iteration, the contents of the array can be thought of as being partitioned into two halves, where the first half is equal to exactly the prefix of elements that have been visited so far, and the remainder is simply a repetition of this default head value. And so at each step in the iteration, we gradually increase the length of the shared prefix, and so by the end of the iteration, the array will have exactly the contents of the sequence, and thus we can verify our program. So, ta-da, we've written a verified program. What exactly did we learn? Well, I guess writing verified code is hard. But unfortunately, the story doesn't quite end there. So this program that I just showed you was actually taken from a real-world OCaml library, and in that library, the implementation of toArray was actually later changed to improve its performance. So here is the old and the new version of toArray, and the old version had to be changed because it has a slightly subtle behavior. The problem is that it actually forces the sequence twice, the first time when it calculates the length, and the second time when it performs this iteration. So if the sequence happened to contain some kind of expensive computation, this implementation essentially executes that twice. So the new implementation avoids this entirely by forcing the sequence exactly once using this fold, and it accumulates the length of the sequence and the contents of the sequence into this OCaml list in reverse. And so when it needs to populate the array, it simply traverses this list rather than forcing a sequence a second time. And so overall, we get a more efficient implementation. The only problem from a proof engineer's perspective is that we now have a completely different implementation, and so our proofs have to be redone. So not only is writing verified code hard, simply maintaining it is a pain. And this is the problem of proof repair, coined by Talia Ringer and recognized by the community. And the question that it asks is, well, can we make this any easier? And so I'm pleased to stand before you today and answer this question with yes, yes we can. We have developed a tool, Sisyphus, that is able to repair proofs of OCaml programs over their changes, and we have evaluated it on a suite of several real-world OCaml programs and their changes, and demonstrated that it is actually able to work on a variety of real-world use cases. So with the motivation aside, in the rest of this presentation, I'm going to present the high-level ideas behind our tool, and then we're going to look at our evaluation. Okay, so let's get started. Remember, our high-level goal is to verify this program with respect to the specification, the old specification. So how exactly do we do this? Well, an observation you may have noticed during our earlier excursion is that proofs in this context are very much syntax-directed. So obvious thing to do, simply take the new program, traverse over it, and map every program statement to a corresponding tactic. As such. The only problem happens when we run into higher-order functions, because, as we've seen, they require invariants. And these can be difficult to find, and mainly because they can't really be easily inferred from the syntax of the program alone. They capture a semantic property. So the key question is, how do we actually fill these in? And more generally, we can think of sort of two key problems that we need to solve. The first is actually generating invariants in the first place. And the second is, even if we've generated invariants, we need to choose an appropriate invariant to fill into our proof script, because if we choose an incorrect invariant, then our proof is essentially useless. So let's look at how we can solve these, starting with the first question: how do we generate candidate invariants? Well, I already told you that the program syntax isn't that useful for generating the invariant, but one thing we do have access to is the old program, and more usefully, the old proof. So why is this useful? Well, let's look at these implementations again. So at a high level, sure, they are different, but if you look a little closer, you'll notice that they have some similarities. For example, both of them have statements where they calculate the length of the sequence. Both of them handle empty sequences. Both of them allocate an initial array, populate it, and finally return it. And the hope is that if we find statements that happen to do similar things, then they might have similar invariants. So, first question, how do we actually discover these similarities automatically? What I've described are kind of semantic properties. Well, as it turns out, we can do this quite easily if we adopt a dynamic-based analysis. The high-level idea is we can work out which program points are similar if they happen to do similar things at runtime. So what we do is we take a randomly generated input, feed it into both programs, and trace their execution, keeping track of which values happen to flow into each program variable. For example, length takes the value 3, and so on and so forth. And we do the same with a new program. And for example, here, size now takes the value 3, and so on and so forth. And now by comparing program points and determining which program points and comparing the values that flow into them, we can automatically determine these kind of similarities. So we can then backport these similarities back to the original proof, and thereby use invariants from the old proof to synthesize invariants for the new one. So we take this old invariant, we look at the expressions that occur within it, and use that to generate candidate invariants for our new proof. And this brings us on to the second problem, which is, how do we choose valid invariants, right? We now have our proof script. It has and now we have a number of candidate invariants to instantiate it with, but which one do we choose? So a kind of obvious idea is you could try and sort of automatically validate these using some kind of SMT solver or automated solver. The only problem is that these kind of tools in this particular domain happen to run in the order of sort of minutes, and we have hundreds of thousands of candidates. So clearly, this is just too slow. Ideally, what we want is some kind of way of quickly testing invariants, i.e. sort of checking if they happen to hold during a concrete execution. The only problem with that is that these invariants depend on logical parameters that don't actually occur anywhere in the program at all. So, and in this case, t represents a sort of prefix of iteration, as we saw with iter_i. So, where exactly do they come from? Well, they actually come from nowhere other than the fold left, from the specification. In this case, the specification for fold left. So let's have a closer look at the proof itself. So I'm not going to show you the proof term for fold left, but we're going to visualize it as a sort of intrinsic proof. So this proof of fold left essentially establishes a certain Hoare triple for fold left, and it does this by sort of symbolically evaluating fold left and establishing at each program point the symbolic, establishing and reasoning about the symbolic state that occurs at that point. And so if you look at these, you might notice an interesting observation, which is, hey, that describes exactly how the values that flow into each invariant are constructed. So if we could somehow take these intermediate states and convert them into assertions, well, then we'd have exactly what we need. So, and that is the key idea behind proof-driven testing. So what do? Well, we take our specification, we instantiate it with some concrete values that we've observed in an execution, and then we use existential parameters for sort of any proofed arguments. And then we reduce the proof term, this instantiated proof term, using sort of standard reduction semantics. This just propagates the concrete values through our proof term. Then we can take this reduced proof term and perform a sort of custom, lightly modified version of sort of custom extraction for coq, and convert this into a piece of executable code that kind of simulates execution of fold left on concrete arguments, annotated with assertions at each intermediate program point for each intermediate program point. So if we instantiate this program with a candidate invariant, we can quickly test whether the invariant holds by whether an assertion is raised during a dynamic execution. So then, returning back to our proof, we can use this to quickly test which invariants are appropriate for our proof scripts and which ones are not. So just to kind of drive the point home, the high-level idea behind our technique is to revisit an age-old idea. Of course, proofs are programs, but what exactly do they compute, right? Traditionally, with Curry-Howard, we consider them as witnessing logical facts. But with proof-driven testing, we adopt a slightly different shift in perspective, and we realize that, hey, higher-order proofs actually describe tests. So, putting this all together, this is the high-level design of our tool. We take as input the old proof, the old program, and the new program, and we produce as output a new proof for the new program. So the way it works is we first copy over the specification, we then traverse over the new program syntax and generate a skeleton proof script. We then use alignment to generate candidate invariants, and finally we use proof-driven testing to test these invariants and thereby instantiate the new proof, leaving a few sort of logical obligations that are unrelated to the heap state and outside the scope of our tool for the user to complete. Okay, so now we've covered the high-level ideas. What remains is the evaluation. So when evaluating our tool, we considered two key questions. The first is whether our tool is effective. Does the human effort in completing the proofs produced by Sisyphus, are they reasonable in comparison to actually verifying the program automatically? And secondly, does it repair proofs in a reasonable amount of time? So to answer this question, we collected a suite of 14 OCaml programs, 10 of these from real-world code bases, such as containers and Jane Street's core. And this is the full set of programs. You don't need to look at this in detail, but the key thing is we selected programs to exhibit a variety of data structures and changes and refactoring. So changes in iteration order, pure to mutable, and things like changes in internal data structures. So let's answer the questions. So first question, is it effective? Our tool is mostly automated, so it may leave some small obligations for the user. Now you can notice that actually in comparison to the time spent to verify the original programs, which were in the order of hours, the time taken to complete the proofs is in the order of minutes. Secondly, in terms of efficiency, this diagram presents the time taken to repair all the proofs, and you can see in the majority of cases it completes in fewer than 2 minutes. Apart from these two extremal cases, if you look at those in detail, you can see that the majority of the time is actually spent in the process of extraction, which is something we haven't particularly optimized. A key thing to note here is that actually testing runs in order of milliseconds or seconds, order of milliseconds, showing the effectiveness of proof-driven testing. Okay, so that concludes my talk. In this talk, we've presented the first automated tool, mostly automated tool, for repairing proofs of verified programs over their changes. And the key takeaways are building blocks from the old proof for the new proof can be found in the old proof. Picking a correct invariant is like the hardest part. And to do this, to facilitate this, we've developed a new take on Curry-Howard, proof-driven testing. Thank you.
All right. So if you have any questions, we have a microphone in the middle of the room. So just walk there and line up for questions. In the meantime, we have one question from Discord, from Talia Ringer. And I like the use of dynamic techniques and testing for proof repairs. Do you think those techniques might be applicable for proof repair back in Coq directly? Or are they specific in some way to embed the program logic?
Sorry, can you repeat?
Okay, so it's just the techniques you present here can be applied back to proof repair in Coq directly, or this is specific to the program logic you use?
So the techniques could be applied back to proof repair in Coq directly, so not within an embedded framework. The key thing is that we need some sort of higher order proof. So anything like induction would work. And so in that case, you could actually use this technique for inferring invariants. So thank you for the question.
All right, thank you. So please state your name and affiliation, and then sorry.
Hi, Tim at Princeton. So can you say more about what kinds of things I saw you had a list of things you had admitted and also the logical, kind of remaining logical tasks that the user had to complete. Can you say a little more about kind of what those tended to look like?
Yes, sure. So actually we have a backup slide. Oh, there's a QR code. Thanks, but it's going to go soon, so sorry. Okay, yes, so the main kind of place where things started to fail and the obligations, so the kind of obligations that were left behind were really things that, properties that weren't present in the old proof. And so these couldn't be sort of handled automatically by proof automation sort of tactics and such. So for example, in one of our proofs, we had this lemma about, our new proof required a sort of lemma about the idempotence of filter that wasn't present in the old proof. And so this was left as an admit for the user to prove. But obviously this isn't too difficult, so only took a few seconds. Perfect, thanks for the question.
Yeah, thank you.
Hi, Charles Averill, UT Dallas. So I'm curious, is proof repair the only application for this technology? I'm more specifically, would it be possible to incrementally change the spec of a program and generate near complete proofs using that technique? I know it's not really the same problem given how you're generating the invariants, but I'm just curious if you've explored this.
Yes, so we believe that the core technique behind proof-driven testing is kind of generic, so it's not particular to this proof repair context. In your particular context of sort of incremental changes, it's likely that the invariants would be very similar, so that might work out quite well. Yes, a sort of more broader application that we're considering is sort of actually just automated verification in general, assuming you have verified combinators. But I think that those would all fall under this umbrella. So yes.
Thank you.
Thanks for the question.
All right, let's thank our speaker again, and we will have our next talk. Thank you.
Okay.